Ooh, some music over there. All right. First of all, a few important things. I just updated our syllabus. So please check it out. And we won't have the final exam. I'm going to combine the final with exam number 4. So you're going to have a very long exam 4, but I'm going to give you 24 hours because you're already at home. It's basically a 24-hour take-home exam. And then you're going to have both the force analysis and chem design stuff in it, right? So the second thing is I posted homework number 5 and project number 3 online. And please make sure you take a look at them. And then I'm going to go over them today and Thursday. And the third thing is I just finished grading your project number 1. And I put my comments in an Excel file on Blackboard. And then I believe the grader is he's going to post the final grades on Blackboard in the next few days. So please keep an eye on it. I think actually your solutions are pretty interesting. When I assigned that project number 1, I was thinking, okay, you have 5 vector loops, then you have 10 equations. You solve all these 10 equations together, but then I think most of you try to solve those vector loops like individually. Okay, so basically you divide the 10 equations into 3 groups and then solve them one by one. I think that's fine, but the problem is it's time consuming because you have to run the Newton-Raphson iteration for 3 times. So that means it's 3 times more time consuming. So that's why I posted a new solution online, and in that code, I solve all these 10 equations in one shot, so it's more efficient. This is going to be extremely helpful for your project number 2, because when you do velocity and acceleration analysis, if you consider those 10 equations as a whole, let me see. So if you, let me mute or, all right. So if you consider all these equations as a whole, then you can directly calculate one single Jacobian, and then you can calculate all the velocity in one shot. If you divide them into 3 subsections, then you have to do velocity analysis for 3 different groups. That's going to be really time consuming. All right. And I also extend the deadline for project 2. I think I give you another 2 weeks. It's going to be due next Thursday, or I might forget. All right, so please check it out, the new deadline. Okay, so the last thing. I try to post all my videos on YouTube, but I don't want to send out an announcement after every single videos. So please, if you want to keep an eye on my videos, please subscribe to my channel. And then just search my full name. I think you can find it. Okay. Because this morning when I check if anyone has saw my energy method video, it seems that the view number is 0. So I think there might be a problem there. But no problem. I'm going to go over these here today. All right. So that's lecture number 15. I already post my notes online. So in this case, we have a crank slider system. And then basically that's a special case for a 4-bar linkage. And then we have the input bar, which has a length of A. We have a coupling bar, length of B. And then there is like offset of C. And then the block is sliding left to right. Okay, so we know the geometries of each link, and we know the density. So you can easily calculate the mass of each link. And then we know that the input bar is rotating counterclockwise in a constant speed of 0.4 pi radian per second. So the question for these is, how can we find the input torque? Like if there is a motor installed at joint O2, what is the T input should be? Okay, so in previous lecture, in lecture 14, we focus on one rigid body. So which means we only have one link in the system. And then you have a motor here. And then you have a torque. And then there is some reaction force over there. And then we already derived the equations of motion. So for a 2D geometry, we usually have 3 equations. One for the linear, 2 for the linear, 1 for the rotation. So in this case, we have 4 links. That means we just draw the same free body diagram, but in this case, just for 4 different links. All right, so that usually the first step is if you choose use Newtonian's method, the first step is always draw the free body diagram. So usually you can forget about the ground because ground is not moving. So that basically all these 3 equations are 0. So you start from the input, and then O to A, and then you have your coupling link. That's your A and B. And then in this case, the last one is actually a block. So you just draw the block. All right. So for these 2D links, a straight link, what you usually have is reaction forces. You don't really care about what these forces are. Just draw the X component, Y component. And then, as I mentioned before, we use a certain naming strategy. We name these as F1 to X and F1 to Y. So the reason why F1 and 2 is we use Fij. I is where this force is from, and J is where this force is ended. So in this case, this force is from the ground link, which is number 1, and then is applied to the input link. That's why the second index should be number 2. So apply the same naming strategy. You have these as F3 to X, F3 to Y, right? Because that force is from the coupler link number 3, and then is applied to this input link number 2. So from 3 to 2. The same thing, you can draw the same force for the second link. And then that's 3 to 3x, 3 to 3y is from the second link to the third. And then this is number 4. So this is from 4 to 3. You have 2 components again. All right. So for the number 4, that's a special case. You only have a reaction force N. Sometimes I use N, and if we use the same naming patterns, then that means it's from ground to number 4, and then it's vertical. And then you also have F3 for X and F3 for Y. Okay. So that's the free body diagram. Oh, one thing I forgot. So for the input link, there is one thing special, which is the input torque. So you have to remember that. So you have 1, 2, 3 free body diagram. For each one, that should give you 3 equations. So for each link, you can just go to our previous lecture and then copy and paste what I did there. So for example, here for number 2 link, we have the X direction. F1 to X plus F3 to X. That's going to give us a linear acceleration. And then along the Y direction, F1 to Y, F3 to Y, that's going to give us the other linear acceleration along Y axis. And then there is always a rotation. And then this rotation is in the XY plane. Okay. So in this case, we need to find all the torque. So you have the T input torque, and then the torque induced by the force 1, 2, and then the torque introduced by force 3, 2. And then all these 3 torques together is going to create a angular acceleration, J2 theta 2 double dot. So these are the equations we need to find out. So next, we need to find out what are the unknowns, what are the known values in these equations.
So first of all, the first thing is actually what are these A's and theta? Because when we talk about linear equations, though, we can pick any points on this link, right? So we can pick infinite number of points on this link, and then, but then usually the rule of thumb is we use the center of gravity, G2, to describe the angular acceleration. The benefit is it's going to save us a lot of time. So we want to know what these A2X is. We also want to know what this A2Y is. And then we want to know the rotation acceleration is easy because it's always theta 2 double dot. So what is A2X and A2Y? That's the first equation we have to ask ourselves. So it's easy to calculate A2 vector because by definition, we can start from displacement vector. So your displacement vector always starts from your O2, starting from a reference point, and ends at the point of interest. And then if you use a complex domain, that actually gives you half of the length times EJ theta 2, right? That's just what we previously learned. And then once you know the displacement vector, so your acceleration vector is just doing the time derivative twice, O2 G2. If you have MATLAB, then MATLAB can help you out. But if you don't have it, then we can, let me directly write it down. It's 2AJ theta 2 double dot EJ theta 2 minus half A theta 2 single dot square EJ theta 2. All right, so this is our acceleration. And then we write it in complex plane. So it has both real part and imaginary part by according to Euler's equation. So the A2X is just the real part of your A2 vector, and the A2Y is the imaginary part of your A2 vector. And then you can see that for this vector is actually simple because your A2 is only a function of theta 2. Theta 2 is your input, so everything is known. So which means your A2, your acceleration is usually known. So that means in your equation, your M2 is known, your A is known. So the only unknowns are on the left-hand side, they are the forces, okay? And then we finish the first two equations, then we focus on the third equation. How about the torque? So what is the T12 then? T12 is the torque introduced by F12. And then when we calculate torque, we need to find the center of rotation. So your center of rotation should be the location where you calculate your linear acceleration. Because in this case, we pick the center of gravity to calculate the linear acceleration. So that's why your torque should be calculated around about the same point. Okay, so by definition, if you can go back to lecture 14, and by definition, the T12 can be calculated as a cross product is the position vector R12 cross product your force vector F12. Okay, so what is this R12? So R12 is a position vector. So it starts at G2. So it always starts at where your torque is calculated about. And then it ends at force location. Okay, so let's see what this F12 is. So in this case, your F12 is applied at joint O2, and then your torque is calculated about G2. So that means your R12 vector starts from G2 and ends at O2. So which means your R12 vector is G2 O2 vector, right? Starts from the center of rotation, ends at where the force is applied. And then we already know O2 G2, we just reverse the direction and then put a negative sign. And then it's minus half A EJ theta 2. All right. And then when we calculate cross product, we just lay out all the entities in a special format. The first row, you put the first vectors in, R1 to X, R1 to Y, 0. F1 to X, F1 to Y, 0. The last row is I, J, K, and then that's your T1, 2. So I, J, K, they're unit vectors along X, Y, and Z direction because we have a one column of 0, so eventually becomes R1 to X, F1 to Y, minus R1 to Y, F1 to, oops, F1 to X, and then actually there is a direction there because the cross product of a vector should still be a vector. But then because we already think that the torque is counterclockwise, so you can actually eliminate this K and then directly write T input plus T1, 2. The reason why we can eliminate this K is because we already assume that this third equation is along Z direction, okay? So you, based on this assumption, you can erase all the direction vectors in the torque equation. So that's your T1, 2. And then your what is that? T3, 2, right? Yep. So can you calculate what the T3, 2 is? So that's the benefit of choosing the center of gravity as the rotation center, because then everything is symmetric. If you look at your F12 and F32, they're symmetric about your G2 point. So that means when you calculate your torque, you don't have to do anything special. You just replace all the subscript from 1,2 to 3,2. So it becomes R32X, F32Y, minus R32Y, F32X. So actually, you're going to see a lot of equations for your force analysis. But then the good thing is most of the time you just copy and paste. You don't have to start from scratch again and again, okay? So this is your T32. And then we need to find the vector, right? So there is another position vector, R32 vector. By definition, we need to find where this thing starts and when this thing ends. So this force is applied at point A. It starts from the same center of rotation. So that means it's from G2 and then ends at point A. I'm gonna point it out. Starts from G2, ends at point A. That's gonna be R32. All right. So that means your R32 is just G2A. And then you can see that is actually O2G directly. And then it's half A EJ theta 2. And then again, the real part is R32X. R32X is the real part of R32 vector. And R32Y is the imaginary part of the R32 vector. All right. So up to this point, you have everything. So you already describe your torque as a force. So that means let's circle out all the unknowns. We have these force unknown, these forces unknown, this is unknown, this is unknown. And you have the T12 and T32, they're also unknown, but then you can write them as functions of force. So they basically have the same unknowns. So how many equations we have? 1, 2, 3. Okay, so we have 3 equations and 4 unknowns. So definitely that's not enough. So that's why we have to move on to the second link and then draw the, and then derive for the other equations, okay? So how about the second link? So we have the two forces on it, 2, 3, and 4, 3. The easy case is actually, let's zoom out. You can directly replace all the subscripts. Let's focus on equation number 1. You can replace the 1, 2 by 2, 3, replace the 3, 2 by 4, 3, and then replace the 8, all the subscript number 2 by 3. Then you have another 3 equations. Make sense? So once you finish deriving equations for one rigid body link, then the second link is going to be really easy. You just replace all the subscripts. Then you're going to have another 4 unknowns, 3 equations, okay? And then the last one is kind of special because in this case, we don't have rotation. You're going to only have 2 equations there. So for this one, let me add 1 page. Oops. All right, so let's focus on the link number 3. Link number 3, if you don't remember. So for the x direction, you don't have to start from scratch. You just copy and paste. Okay, your 1, 2, right now it becomes 2, 3. And then your 3, 2 right now becomes 4, 3. And then it's no longer link number 2, it's link number 3. And then the acceleration is a3 then. And then the same thing for y direction. You have your f23x, oh sorry, f23y, f43y equals to m3a3y. And then the rotation is going to be t23 plus t43. That's going to give you another rotation, angular acceleration. Okay, and then you just follow the same method. Your t23 should give you r23x, f23y minus r23y, f23x. Again, you just copy the equations from previous step. You see that your t32 has all the subscription of 32. And that means your T23 should have all the subscript as 2, 3. Okay, and then you can copy and paste for the 3, 4, for the 4, 3, sorry. And then it's R43X, F43Y, minus R43Y, F43X. It's a lot of copy and paste. Just pay attention. Don't mess up with your subscripts. So that's your link number 3. And then let's focus on all the unknowns. So these is unknown. The same thing. And then how many equations we have? We have number 4, 5, and 6. So we have 8 unknowns and 6 equations. And then the situation is getting worse. But no worries. We just keep deriving, to keep finding other equations. For the link number 4, for the x direction, so you only have one force along the x direction. So that's F34x. That's going to give you a linear acceleration. For the y direction, these 2 forces should be balanced. So you have your F34y plus F14y equals to 0. And then there is no rotation because it's a slider. So in this case, let's check how many equations we have. So this is your unknown, this is your unknown, this is your unknown. And then how many equations? 7 and 8. Okay, so let's check 1, 2, 3, 4, 5, 6, 7, 8. We have 8 equations. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 6. We have how many unknowns? We have 11 unknowns. So 11 unknowns and 8 equations. All right, so that means we're missing 3 equations. So all the additional equations are from the Newton's third law. So which means we have 1, 2, and we have like joint A and joint B. So that means the force at joint A and joint B, they should be the same amplitude, but different direction. So these additional equations are at joint A, you should have F23x equals to F32x minus F23y equals to F32y. And then at joint B, you should have, let's see, F43x equals to F34x, and then F34y equals F43y. Am I missing anything? Let me see. One, two. Can you see why I have an additional equation? I think I missed something here. So then you have your equation number 9, 10, 11, 12. You should only have 11 equations, so one of these might be redundant. Let me check it out. One, two. Oh, I see. I think what I'm missing here. I forgot to circle out your T input is actually unknown. So we actually have 12 unknowns. So that's why we need to 12 equations. All right. So eventually you have 12 equations, 12 unknowns. And then luckily all these equations are linear. So that's why you have to arrange them into a matrix format and then solve them in MATLAB. And already give you the matrix in the attached notes. So let me know if you have any questions. Okay. Hello. All right. So that's cool. I think the Newtonian method is pretty natural, but it's not the best one when you're trying to calculate the torque. So that's why I'm going to teach you another trick, is the energy method. Okay. One thing you have to think about this is, in this case, we ignore, if we ignore the gravity, but what if we want to include the gravity? What if I told you that, okay, there is a gravity downward, and then the G is 9.8 meters per square second. Yes, correct. So if you have a really weird shaped link, then definitely I would suggest you to find the center of gravity again. And actually that's part of your project number 3, I believe. One of the coupler link is a triangle, and then you have to find the center of that gravity first. But no worries, we're gonna go over these on Thursday when I'm gonna give you some weird links. Yeah, we have to know the mass. So the mass is already given, right? So we know the geometry, we already know the density, and then we know the acceleration g. Then we are gonna know all the gravity forces. So then what? Then let's see what we already know. So that means your g is always along the y direction, right? So if you want to include the acceleration, or I mean, if we want to include gravity into the equation, the only place you need to make change is all the y direction equations. You have to add the gravity force to the left-hand side, right? Just change your number 2, number 5, and number 8. Make sense? All right, so let's move on. Energy method is, I believe, is going to be the method you'll love the most. Okay, so previously we mentioned that in this case, let me draw these 4-bar linkage again. It's a crank slider. It's rotating at constant speed, theta 2 dot. So what are the energies in the system? So when we calculate energy, is, let me see. The energy is the kinetic energy plus the potential energy. So for this class, when we talk about potential energy, we're only looking for 2 things. Any spring force, or any gravity. So in practice, there are multiple ways to store energy. So you can actually store your potential energy in magnetic field, in electric field, in pressure. So, but to simplify our discussion here, we only talk about spring force and gravity force. So in this case, let's first talk about what if we have no gravity situation. Okay, so we assume that there's no gravity. The gravity of the system is negligible. So that means this gives us your E equals to kinetic energy only. So what are the kinetic energy? As I said, your kinetic energy equals to T linear plus T rotational, right? So you have both linear motion, rotational motion. So that's why your kinetic energy has 2 components. So let's see, you have number 2, number 3, and number 4. So your T is the summation of T1, T2, T3 plus T4. So the subscript 1, 2, 3, 4 describes the which link you're looking at. Your ground link is always stationary, so that's why the first term is 0. So you focus on your T2, T3, and T4. And then what are they? T2 equals to half of the linear motion, and then half of the angular motion, right? The same thing, you have your T3 equals to half M3 V3 half J3 theta 3 dot square. Copy and paste, half M4 V4 square plus half J4 theta 4 dot square. So that's another no-brainer, just copy and paste. Find the mass of this of the link, and then find the moment of inertia of the link, and then find the linear speed, angular speed, and remember all these speeds are around the center of gravity. Okay. So several things special for this case. Your link number 4 only has linear motion. It's not rotating because it's slider. So that means the last term is gone. Okay. So then up to this point, we know the kinetic energy. Is this kinetic energy a known value or unknown? So is T known? or unknown. Yeah, it's already known, right? Because we just need to know the velocity. We just need to know all the velocities in the system. You can easily get these from velocity analysis. All right, so that means it's known. So if T is known, so that means your total energy of the system is known. So according to energy conservation law, so if this system is not doing any work, that means the total energy of the system should maintain the same as always. The only way you can change the total energy E is by doing work to the system, right? So that means the variation of your energy equals to the work done by external force or torque, I should say. Okay. So if you want to change the total energy of your system, you have to do some work. All right. So the variation is really hard to define, but then we can easily define the changing rate. So that means your E single dot equals to dE dt, which means how your total energy changes with respect to time. The changing rate is going to be the changing rate of the work done by external excitations. So the changing rate of work, based by definition, is power, right? So that means power generated by external excitation. So one thing we have to pay attention here is how to define the external. So to simplify this discussion in this class, when we talk about external, that means all the forces provided by the ground and all the forces or torque provided by the actuator. So let's see. So external means number one, by the ground. Number two, by the actuator. So that means is either like hydraulic pump, either a motor or anything else. So any motors or actuators driving the system is going to be considered as external. And then the ground force is also going to be considered as external excitation. So we know the T3, 4. The first thing, so that means in order to find this equation, first thing we need to calculate the changing rate of E, right? We need to find what the dE dt is. So the angular speed part is straightforward. It's J2 theta 2 dot theta 2 double dot plus J3 theta 3 dot theta 3 double dot. You just calculate time derivative for the for these two rotational terms. But then how about the acceleration, linear kinetic energy? So let's take T2 for example. T2 linear for example. Your T2 linear is half m2 v2 square. We know that m2 is constant. This is constant. The only thing that is time varying is your v2. But then your v2 is actually in absolute symbol. It's really hard to calculate these, right? But then in calculus, your kinetic energy can also be written as the product of two vectors. Make sense? That's because your v2 vector length square equals to v2 product dot v2. And then we can use vector calculus. I'm not sure if you already learned this in your calculus class, but then by definition, dt2 linear dt is going to equal to half m2 v2 vector dot product A2 vector. Here, your A2 is your acceleration, linear acceleration. So which means, oh, sorry, I forget one thing. The coefficient should be gone. Okay, so then you have your M2, V2, A2. Remember that's dot product. M3, V3, dot product A3, plus M4, V4, A4, dot product. Yes, correct. So no matter which method you're using, no matter it's Newtonian method or energy method, if you want to calculate force, you have to complete position, velocity, acceleration beforehand. Sorry, that was my daughter. So, okay, so where we are right now. So do you want me to go over the definition of dot product, or you already know that? So that means, I think I can briefly go over that. When you have a vector, so your vector has both x component, y component, A3, you have your x component, y component. The dot product of two vectors is actually a scalar, V3, A3 dots. You multiply the first pair of entity and plus the second pair of entity. All right, so that's your dot product. So let's see, let's focus on this equation. I'm gonna circle it out. Okay, as I mentioned before, 1, 2, 3, 4, 5, we have 5 terms on the right-hand side, but then the good news is they're already known. They're all velocities and accelerations. We can get these from position, velocity, acceleration analysis. On the left-hand side, we need to find out the power generated by the external excitation, right? So these are all known values. That means your E dot is known. The second part we need to find is what are the external excitations? What is the power? So in this case, how many external excitations we have? Can you find all the external excitations? Well, it's actually more than one. So let's look at all the ground joints. So I'm going to use a purple color. So your F1 to X, that's an external force. Your F1 to Y, another external force. We have a T input, that's your external torque. You also have a supporting force there, that's F1 for Y. 1, 2, 3, 4. We actually have four external forces and torque. All right, so let's see how much power they each generate. Your F12, because your O2 joint is fixed, you're applying a force to a fixed point, so you're not going to do any work. Okay, so that means these two forces give you no power. This one for Y is going to give you is a force, but then it's also moving. But then the moving direction is perpendicular to this normal force. So that's why it also gives you no torque. No power. So the only thing that gives you an input power is the input torque over there. So that's why your external power equals to T input times displacement. Oops, what happened? So this displacement is tricky. If you have a torque in front, then the displacement is going to be an angular displacement. If you have a force in front, then you have a linear displacement. In this case, the displacement associated with T input is your theta 2, right? Because your T input is cranking the input link, and then displacement is described by theta 2. So that's why you have your T input times theta 2. Sorry, I think that's velocity. I need to change that. That should be velocity because it's power, is not energy. So that's why this should be theta 2 single dot. All right. So we know that the external power should be equal to E dot. E dot is already known. Your input speed is known. The only unknown in the system is your driving torque. So that means you can directly get a driving torque in one shot. That's the power of energy method. So remember when we do Newtonian method, we have to find 12 equations. They're pretty long and difficult. But then in here, we just need one equation, and then we can get the T input in one shot. But then the drawback is you're missing all the intermediate force information. You can only calculate a T input. There's no way you can calculate the force at each joint. So for example, if you want to in the future, if you have designed a crank slider and you want to know, okay, if my link number 2 is strong enough to survive in that driving force, then you have to go back to Newtonian method again. You cannot use the energy method. All right, make sense? All right, okay. So a few changes. So here we have few strong assumptions. There's no gravity. There's no friction on the slider. So case number 2, let's see if I have time for discussion. Okay, I think we can discuss this case number 2 here. If there is friction at the slider, or the coefficient mu equals to 0.2. So let's see, you have a crank slider 2, 3, 4, and right now it's cranking to the left, and then let's assume number 4 is moving to the left, and then there is a friction force F applied on this number 4. And then no gravity still. All right, so this friction force is F1 for Y times mu, right? That's the friction coefficient. Can we still use energy method to solve this problem? Well, it's not true. Let's go back to the very first equation. Along the y direction, F3 for y equals to F1 for y. So there is a normal force introduced by F3 for y. If you look at here, that means the coupler link number 3 is going to drag the slider. So the dragging force is going to introduce a normal force. So let's see, what is the total energy of the system? It's still the same, right? If you look at the kinetic energy, potential energy, adding a friction doesn't change those energies, right? So your E should be the same E. But then how about the force? How about the power generated by external excitation? So we know that it has T input theta 2 dot. That's the power generated by the input torque. But then here, your friction is also introduced by the ground. So you should consider your friction as an external force. So that means plus friction times the velocity, right? And then your T input theta 2 dot plus F1 for Y mu V for X. So you only have one equation, but in this case, we don't know the normal force. We don't know the input torque. So personally, I think energy method cannot help us to solve this problem unless you have any better ideas. So I don't think we can solve this because we have two unknowns, only one equation. So that means you have to go back to the Newtonian method, and then you need to make some changes to the last equation you have, to the equation number 8. So if, let me use the purple color, if there is friction, so your y direction equation number 8 should become, oh, sorry, actually that should be x direction. Your x direction equation number 7 should become F3 for x plus the friction equal to M for A2x. Or I should use negative to consider the direction of the friction. And then your friction is F1 for y times mu. Make sense? Then you have one more unknown, but then you also have one more equation. You have 13 unknowns and 13 equations, but then you can solve it. So that's the other drawback for energy method. So it doesn't always work. Usually when you only have one external excitation, that method works. But if you have more than one, then you have some kind of relationship, but you cannot solve it. Make sense? But then project number 3 is actually special. I'm gonna go over more details on Thursday. So for project number 3, I believe we have a triangular shape like this, triangular coupler. There is a constant point force P, which is downward. But then in this case, you have your T input, and then you have your force excitation, which is a linear force. But then in this case, you can use energy method as still, because your P point force is a known value. If your P force is known, then you can use the energy method to find your T input. Okay. So the other way to say it is, if your friction F is given, if we know how much friction force is there, then we can still use energy method. All right. So I think I'm gonna end it here, and I'm gonna give you one more case to think about after the class. Case 3, using energy method. What if we consider, oops. Energy. What if we consider gravity? So the same problem, but then there is a gravity going down, G. Can we use energy method or not? Yep. In this case, definitely yes, right? Because we're giving it a potential energy only, and the potential energy should be a known input. All right. So I'm gonna give you. I'm gonna post the solution online for this case number 3, and then please take some time to think about it more. All right. Any questions? Okay, great. Yep. Nice to talk to you all.